In this video, we will discuss Green's theorem, which is another multivariable version of the fundamental theorem of calculus. Before we can state Green's theorem, we need to define a few terms. So first, a given parameterization R of t of a smooth curve C gives an orientation or a positive direction along the curve. So if we have some curve, let's say C, then we can have that curve start at some point, say R of A, and finish at some point, say R of B. And then the direction going from A to B is going to give us the orientation of our curve. Now, if we move in a counterclockwise direction, then by convention, we will call that positively oriented. So if our curve is parameterized by R of t and that moves in a counterclockwise direction, we're going to note that as being positively oriented. Second, a curve C with position vector R of t is called smooth if the components of R have continuous partial derivatives with respect to t. So if we have a parameterization R of t, we can take derivatives, and those derivatives are continuous, then we call that curve smooth. If the curve C consists of a finite number of smooth curves joined at consecutive corner points, then we say that C is piecewise smooth. So for example, we could start at a point and then we could have a smooth curve that ends here, and we'll call that C1. And then we could have a sharp corner that would not have a continuous partial derivative at that point, or a continuous derivative at that point. So we could have a corner there, C2, and then we could have another corner that before we define C3. And since the curve C, which joins C1, C2, and C3, has a finite number of smooth pieces, we call that curve C piecewise smooth. So think about C as being kind of the sum of these two curves as being piecewise smooth. And then finally, the curve C parameterized by R is called closed if the initial point R of A equals the initial point R of B. And it's called simple if it has no self-intersections. So if I draw a curve like this that starts and ends at the same point, so here we have that R of A is equal to R of B. Okay, then we have a curve that is closed. But it does not self-intersect, so we also say that it's simple. But if you make a curve like this, it's like maybe a giant 2, okay, then that curve is not closed. The starting and ending points here are different. And it's also not simple because it intersects itself. Okay, now that we have these terms, we can move on to our statement of Green's theorem. Green's theorem says, let C be a positively oriented piecewise smooth, simple closed curve that bounds a region R in the plane. So the picture that I want you to have is the picture here on the right. That's this picture right here, where C is positively oriented. See, it moves counterclockwise. And it is closed. It happens to be smooth here. And it bounds a region R in the plane. Okay, so C is like the boundary, R is the interior. And then suppose that F is a vector field, PQ, and that P and Q have continuous first-order partial derivatives on R. So both P and Q are differentiable. They both have partial derivatives that, with respect to x and y, that are continuous. Then the integral over the closed curve C of f dot dr, which can be rewritten as the integral of p dx plus q dy, we've seen that notation before, is equal to a double integral over the region R of dq dx minus dp dy dA. So this is Green's theorem. Okay, so it's was proved by the mathematician Green. Okay, so it's not named after a color. That's actually the name of the mathematician. Okay, and what it's saying is essentially, and this is kind of a strange thing to think about, but what it's saying is that if you do a double integral over what seems to be some funny looking derivative of my vector field f. Okay, so this is not the derivative of f with respect to x or the derivative of f with respect to y. It's this funny looking derivative where we take the derivative of the second component with respect to x minus the derivative of the first component with respect to y. So it's this funny looking derivative. And if we integrate that derivative of f over the region R, then one way that we can integrate that is we can evaluate that by integrating around the boundary. And that's what makes this kind of like the fundamental theorem of calculus. Because the fundamental theorem of calculus says that we can integrate a derivative by evaluating the function at the two endpoints of the interval, the boundary. Okay, so this is saying we can integrate this funny looking derivative and we can evaluate the integral of this funny looking derivative by integrating around the boundary. So the evaluation of the integral of a derivative has to do with doing something to the function around the boundary. In this case, it's doing a line integral around the boundary. Now, some of this will become a little bit more clear as we continue through our journey in vector calculus, because we will define what this funny looking derivative is here in a future video. Okay, but for now, let's just think about this as being like a fundamental theorem, saying like, how do you evaluate this integral of a derivative? Well, you have to look to the boundary. Okay. Well, now I would like to prove to you Green's theorem. And instead of proving Green's theorem in generality, what I'm going to do is I'm going to give you an argument that works for a type 1 region. And then you'll be able to see that a similar argument works for a type 2 region. And you'll recall that all type 1 and all regions can be rewritten as type 1 and type 2 regions. So we can break them up into type 1 and type 2 regions. So essentially, I'm going to prove Green's theorem with a special case, give you an idea of how the argument works, and then you can imagine that I'd have to continue working through a few of these special cases and then add them together to get the full Green's theorem. Okay, so what I want to do is I want to show two things, okay? The first thing I want to show is that if you were just to integrate p dx around a type 1 region, then it's equal to minus the integral over r of dp dy dA. So essentially, I'm going to show a piece of Green's theorem. I'm going to show that if you integrate this piece, that you're going to get the double integral over that piece. Okay, so that's the first thing that I want to show. Okay, and then the second thing that I want to show is that if I integrate around c q dy, that I'll get the double integral over r of dq dx dA. So in this instance, I'm going to show if we integrate this, that it's equivalent to doing the double integral of that. And then you can put the two pieces together, and that shows all of Green's theorem. So the first thing that I want to show is I want to show 1, and I'm going to do that over a type 2 region. Sorry, a type 1 region. Okay, so 1, the thing I want to show in 1 is going to work over a type 1 region. The property 2 that I want to show is going to work over a type 2 region. So what I've done is I've drawn a type 1 region for you. So we'll remember that this is our kind of our general type 1 region. So basically, the lower edge and the upper edge are defined by two functions, g1 and g2 of x, right? And then the left and right edges are vertical lines. Okay, so let's try to do the double integral of dp dy. Okay, well, I'm going to just write it out. That's going to be the integral from a to b, and then the integral from g1 of x to g2 of x of dp dy dx. Okay, so I'm integrating from the lower function g1 of x to the upper function g2 of x dy, and then in x's I'm ranging from a to b. Well, I can easily do that first inner integral because I'm integrating dp dy. So that just gives me p. So if I integrate this, I get p, and I need to evaluate that at the two endpoints. So this is going to be p of x g2 of x minus p of x g1 of x dx. Okay. So now what I want to do is show that I want to show that the integral of c of p dx gives me the same thing. Okay, so the integral around the entire curve c, which is the integral over c1 plus the integral over c2 plus the integral over c3 plus the integral over c4. Okay, I'm going to show that that gives me the same result. Okay, so I'm going to parameterize the curve C1 by x g1 of x. So I'm going to let x be my variable here just to make it easier. Okay. Then what do we get? We get that the integral over c1 of p dx is equal to, well, we're going to integrate from a to b. So we're going to integrate x from a to b, and then we would be integrating p of x, g1 of x, dx. Okay, so that is our parameterization of c1. That gives me that first part of the integral. Then I'm going to parameterize c3, but I'm actually going to parameterize minus c3 because we're imagining that c3 would go still from, or c3 goes from right to left, but I'm used to forming these things from left to right. So I'm going to parameterize minus c3 by x g2 of x. Okay, then I've got the integral over c3 of p dx is the integral. Well, the integral of c3 is going to be minus the integral over c3 going the other direction of p dx. And in that case, that's going to be minus the integral from a to b of p of x g2 of x dx. Since we parameterize by x g2 of x, we substitute that into p, and then minus c3 does go from a to b, going from left to right. Okay, so I've now computed this integral over c1, and I've computed the integral over c3. What about that c2 and c4? Well, I'm going to note that dx equals 0 for both c2 and c4. Okay, so look at these vertical paths here, okay? And that there's going to be no change in x there, right? We're only going to change the y. So the dx is 0 in both of those cases. So now we have dx equals 0 for c2 and c4. So that means that the integral around c2 of p dx equals 0, and the integral around c4 of p dx equals 0. So what do we have is, finally, is that if I integrate around c p dx, then that would be the sum of the integral of c1 p dx plus the integral of c3 p dx. That's going to be the integral from a to b, because both of those turned out to be integrals from a to b, of, well, p of x g1 of x. So I'm going to combine these into one integral, and then minus p of x g2 of x dx. And in fact, that actually is going to show our result, because if you look at this integral, okay, that's actually equal to minus this integral. So minus that integral is going to be minus dp dy dA. So this is equal to minus the double integral over r dp dy dA. And so what I have shown is exactly what I set out to show. I have shown 1, that the integral around C, okay, that's around that closed path. I forgot to put that in there. Of p dx is equal to minus dp dy dA, as long as I'm integrating over a type 1 region. So now I want to make one final comment. That comment is about type 2 regions. Okay, so if I want to integrate over, or if I want to show number 2, so I'm going to show that the integral of C over C of q dy is equal to the double integral of dq dx dA. If I want to show that, what I do is I do essentially the same proof, okay? But now over a type 2 region. So I'm not going to go through all the details. I call this a shampoo proof because I always say rinse and repeat. And then I'm going to rinse and repeat with a type 2 region. Okay, and that will prove 2. And once you've proved 1 with a type 1 region plus 2 with a type 2 region, that will actually help you prove the general theorem for a general region. So piece together 1 and 2. For a general region. Okay, so what I've done is just giving you a glimpse into how you prove Green's theorem, and that is just by proving Green's theorem, at least one half of it for the type 1 region. You would have to then prove the other half of it for a type 2 region, and then piece the two together for a general region.